Hi, everybody. I hope everyone had a good weekend. Today is week 7. Holy crap, it's already the 7th week of class. Like, when I was typing that in there, I was like, is it really week 7? I didn't make a typo, did I? No, we're like 60% of the way done with the quarter. So, the quarter's almost over. We're in the back half of the class. That does mean that the content does ramp up pretty quickly, so I hope that people are keeping up. Today is also election day. Make sure that if you are eligible, that you go out and vote. drop off your ballot at a drop box. Very important. Support democracy. What are we doing in Chapter 11? Where is my slideshow? There it is. Oh, we're naming stuff. Yeah, this is the naming chapter. So, this is how we name molecules and formula units and all sorts of stuff. You're going to see a bunch of compounds that we have studied in Units 9 and 10. And then you're going to see a new one at the very end. We're going to talk about naming acids, because acids are really common. And we use them a lot in chemistry because they have useful properties that do things that we want. So you need to be familiar with those. So, yeah, that's the overview. There's not really much to say about it. We're going to name stuff. We're going to start by just categorizing things so that we know which of these 3 categories to name. So if I go to the tablet here, and I'm going to just circle this guy. Oops, that's not a very good circle. That's good enough for now. The first section, what we're going to do is we're going to learn to categorize a compound. And we're going to use one set of rules for a given compound, okay? The first thing that you need to do is figure out which category does your molecule go into. If you do that incorrectly, then you're kind of stuck, and you're going to use the wrong rules, because all the rules are different. Your task will be to, again, get that molecule in the right category, and then apply the rules correctly, okay? So that's the focus of this week's lectures. We're going to do this today, and we'll probably finish it up on Thursday. All right, so what is the name of the rule set that we use? Well, it's called nomenclature. So you may hear this term thrown about when you say, okay, it's time to talk about nomenclature. That just means we're going to name stuff. Okay. Now, this is a systematic set of rules. What this means is that we can apply these rules to any molecule and get a name for it by following a system. There are no common names here. So common names would be things like water, or acetone, or alcohol. Like, these are all names that we came up with because these compounds are common. We see them all the time. So we're just going to give them a name that's simple. Like, you don't want to say, oh, I'm thirsty. I'm going to go get some dihydrogen monoxide from the dihydrogen monoxide fountain to replenish my missing dihydrogen monoxide. Like, that's dumb. Like, you don't want to say that many syllables, right? So we call it water. Or we call it H2O, or whatever. Those are common names. Whereas the actual systematic name would be dihydrogen monoxide, because there's 2 hydrogens and an oxygen. And you're going to see that these rules apply in a very simple way. But common names ignore all of those rules. So we're going to skip over common names and not really talk about them, because there's too many compounds to use common names. We're going to use systematic rules. Now, each of the systems that we're going to use, in other words, each category, is going to have unique rules. Now, if you use the wrong rules, you're going to get a name that's slightly wrong. It doesn't matter if it's slightly wrong, it's still wrong. Be careful, okay? If you use the molecular rules for the ionic compounds, then you get something that's wrong and doesn't make any sense, and nobody will understand what you're talking about. So be careful. Like we said before, the first category, or the first step, is always which category does something belong to. So we got to figure that out. Here are the categories. These 2 categories right here, I'm going to highlight them in yellow, are actually the same category. It's just that I put in polyatomic ionic compounds separate because they're a little bit easier to work with, but they do still follow the ionic rules. Binary molecular, aka covalent compounds, follow their own rules, and then acids are special. Acids follow their own rule. Now, how do we identify these things? Let's start at the top here. We know what an ionic compound is because we've studied that. In fact, I've tested you on that. What does an ionic compound have? It has to have a metal and it has to have a non-metal, right? So there you go. If you look in your compound and you see that there is a metal that is serving as an ion, it must be ionic. Now, if you see a polyatomic ion, same deal. So this includes ammonium, and then any other polyatomic ion that you have studied and presumably memorized, but let's be real here. It's an online class. You don't have to memorize it. If your compound is covalent, it's only going to have nonmetals in it. We're going to only use 2 nonmetals at a time. So you're going to see this word here, binary. Binary just means 2. There are only 2 things. The same is true up here for ionic compounds. We're only going to study binary ionic compounds and name them. Because you could make ionic compounds at any ions you want to. But we're going to just name the ones that have 2. And then the last category, acids here, have some special properties that I'm highlighting in blue here. Acids contain what's known as the hydronium ion, which is H+. Technically, that's H+ bound to water, but for our purposes, H+ is fine. And anytime you write a formula that starts with H, H is the first thing listed, it's an acid. Now, of course, there are some exceptions, like water. We'll talk about water and why water is kind of weird in terms of all these definitions, because water is so abundant. We've actually defined a bunch of things around water, and that makes water kind of like the midpoint or the breaking point of a lot of these rules. But for our purposes, if you see something that starts with an H, it's an acid. We're going to use the acid rules. So I'm going to put a bunch of compounds on the screen here, and what I want you to do is, using the rules on the previous slide, remember you can go back in the video, you can pause and rewind even while live. I want you to categorize each of these formulas as either binary ionic, binary molecular / covalent, or acid, okay? You can number them 1, 2, 3 if you'd like. In fact, I'll do that on the screen. And then type your answer in the chat once you have identified your choice for each of them. I'll give you just a second to do that. While I sit here and drink water. 1 is an acid. Good, that's a good start. That's right. Actually, while you guys type that out, I'm going to go close my back door because it's cold. So I'll be right back. That's not how I mute the mic. Hold on. Alright, sorry about that. I got distracted by cats, because of course I did. Alright, so we got 1 is an acid, that's right. Where's my pen? There's my pen. And we can identify that because it starts with H. 2 is binary molecular. Because it only has, not nom. That's what you do when you eat something. Because it only has non-metals. And then 3 is binary ionic. Because it contains a metal. And a non-metal. All right, good. There you go. So that's how you categorize compounds. That's literally the first step that you're going to do for everything in this chapter. Whenever you see a compound, first step, which is it? Binary ionic, binary molecular, or acid. Categorize it correctly, and then apply the correct rules. I don't know why that slide appeared twice. But it did. Weird. Okay, I'm going to have to go and fix that. Alright, so there's some more for you to categorize. So let me number them again for you. Because this seems like a really, really obvious thing to do, and trust me, this is important enough that I'm gonna go over it for 10 minutes. Make sure that you are categorizing it correctly. So categorize these. We'll go over the answers in just a second. Alright, just one more minute to finalize your choices. Type them in the chat if you'd like. We'll go over the answers together soon. All right, so let's go over what we got here. So for number 1, we've got iron and we've got sulfur. Iron's a metal, so that's going to make this binary ionic. Number 2, we got this in the front. Easy enough, it's an acid. Number 3 and 4, we have polyatomic ions all over the place. So these are polyatomic ionic. Number 5, we got selenium, but selenium's a nonmetal. So that makes this, binary molecular or covalent. Number 6, there's our H. That's an acid. And then number 7, we got rubidium. Rubidium's a metal, so that makes it binary ionic. There you go. That's how we categorize elements. Or not elements, I'm sorry. How we categorize compounds. Any questions, let me know. All right. For most of the first part of the lecture, we're going to do ionic compounds because there's the most things in them. And I listed them first, so that's why we're doing them first. So let's talk about ionic compounds in a little more detail. What you see on the screen is the rule for naming an ionic compound. Now, all of these are going to be binary or polyatomic, but the rule's going to be the same more or less. On the left in red, you have the cation. And on the right in blue, you have the anion. You're going to take the appropriate name for those things and plop it in the box. And that's it. That's how you name it. There are no other additions that you need to do. Name the metal, name the nonmetal with "ide." Easy as that. Now, let's break down each of those boxes into more important detail. Because there are some caveats within these simple rules. Because if there weren't, everybody could name compounds. It'd be really easy. Okay. So what is a metal? First of all, a metal is just an element on the periodic table that is to the left of the metal nonmetal line. We studied that in the Ionic chapter in chapter 9 when we talked about ionic bonding. Okay. What are the names of metals? Well, you just look at the periodic table and take the name straight off it if, and the if is important, if the metal is in group 1, 2, or is aluminum. Now, depending on the text that you were reading, you'll note that there are some exceptions that are included here. So your text might say that gallium, zinc, cadmium, and silver are all also part of this. I'm not going to test you on that. I'm only going to test you on these, group 1, group 2, and aluminum. If you are using one of those metals, again, in group 1A, 2A, or you're using aluminum, you just write its name. The reason that you're writing its name is because those elements have what are known as fixed charges. They follow the octet rule. So even though sodium has a +1 charge, it will always have a +1 charge, and therefore you don't need to worry about mentioning its charge in its name. When you say sodium, it's always sodium as +1. Now you might be thinking, well, okay, then the charge must be important, and it is, because for any other metal, if you try and name it, if you just said iron, then you end up with ambiguity, and I'm going to show you how that works in a second here, once I get the right color. My stylus is not tapping the screen correctly. There we go. So let's suppose that I had these compounds, FeCl2 and FeCl3. Now, based on what we studied in the ionic compound chapter, we know that Cl is always a minus in an ionic compound because that's how it gets the octet rule. It needs one electron, and it gives it a minus charge. Since I have two of them, this iron must be a +2. Same thing over here, except this iron is +3. How do I differentiate between the two of them? I can't just say iron chloride for both because that would be ambiguous. They're different. In fact, they're even different colors. If I gave you iron 2 chloride and iron 3 chloride and put them on a plate in front of you, you would be able to tell which one was which because they're different colors. So what we need to do is we need to indicate the charge for a variable charge metal, which would be any other metal that is not the ones listed above. And we need to include the charge as a Roman numeral. So this guy right here, Fe2+, becomes iron with a parentheses and the Roman numeral 2. That would differentiate it from this iron right here, which would be iron, parentheses, Roman numeral 3. Now, just in case you aren't aware of all of the Roman numerals, we'll go over them. Oops, this is kind of... Let me just do that real quick. There we go. Just in case you aren't aware of what all of the Roman numerals are. Oops, I can't see this because it's behind my... Can I do that? Yeah, okay. So let's see here. So we've got our numbering system. Oops, that's not a pen. There we go. We use the Arabic numbering system, which is awesome because it's base 10. And the other numbering system is the Roman numbering system, which is not awesome. Roman numerals are only used for 3 things. One is Final Fantasy games. The second is the Super Bowl. And the third is naming ionic compounds. So, otherwise, Roman numerals are completely worthless to you. But here's the way that we translate Roman numerals. So, we got 1, 2, 3, 4, 5. We're not going to go past 8 in this class, but I'll go down to 10 in just a second here. So the Roman numeral for 1 is I. For 2, it's II, as in like you're a pirate. And then 3, you become Desi Arnaz, which is I. 4 is IV. 5 is V, because reasons. 6 is VI. 7 is VII. And 8 is VIII. And then we'll go down here and do 9 and 10. We won't use 9 and 10 because charges just don't get up higher than 8, generally speaking. Now, do you need the bars on the top? No. You could instead draw them like this if you'd like. There you go. It's just that if you put the bars, people will know, oh, those are Roman numerals for sure. Whereas if you just put this guy up here, people might be like, oh, what's this 1? Because not everybody writes a 1 like this. So those are the Roman numerals. And we're going to use them for naming metals. So let's actually assign some names to... Oh, we got to name nonmetals. Of course we do. I thought we were going to name metals. We're going to do that in a little bit. So how do I name a nonmetal? Now, we don't actually follow the same rule as metals. We don't just say, oh, it's got sulfur in it, so we're going to call it sulfur. When you have a nonmetal, we're going to split its name into two pieces. The first is going to be a stem, which is a part of the original name. And then the last part of that is going to be "-ide". Now, which parts of the name become the stem and which parts are discarded so that we can put "-ide" on depends on what element you have. However, you have probably heard most of these and not realized that there was a difference. So, for example, if I have chlorine here, I gotta get a different color because this is gonna overwrite my ion there. So here's chlorine, Cl. That's chlorine off the periodic table as a neutral atom. But chloride has this minus charge here. Okay? "-ide" is used for ions only. Now, where is this list of "-ide" anions? I believe it's in your text. I don't have it in the slides, but you've probably heard of these already. So as we do them, you're going to just naturally append "-ide" to things and be like, oh, okay, yeah, I've seen that. All right, so let's do some examples here. So here's KBr. And what we're going to do is we're going to name the metal and then name the nonmetal. So first, name the metal. What is this called? And then name the nonmetal. So we got potassium. That's good. Potassium is in column 1A, group 1. So it's fixed. We only call it potassium. This is bromine, but we name it with "-ide, so instead of bromine, it becomes bromide. Bromate is something different, so be careful. Bromate is a polyatomic ion. All right, let's do another one. What is this? So we got sodium. And we got oxygen, but oxygen loses most of its letters and becomes oxide. Which everybody's heard of oxide. Probably not even in a chemistry context. You've just heard that word thrown around because it sounds cool. Now, you'll notice that at no point did we ever say, oh, there's two of these. Should I put something else in here? No. There is no rule that says that. All you do is name the metal and name the nonmetal with "-ide. You ignore all the numbers. And there's a reason for that. The reason being, if I have sodium and oxide and I put them together, there's only one compound I can get, and that's this, right? If I put one of them together, I would have that, and that's not an ionic compound. That's an ion. That's a polyatomic ion, actually. So there's only one orientation of ions for a given ionic compound name. Therefore, you don't need to worry about numbering how many there are. Okay? And in fact, you can't number how many there are. If you wrote disodium oxide, that is wrong. It would get flagged as incorrect, and people wouldn't know what you're talking about. Because sodium and oxygen combine together in only one way, and that's sodium oxide. All right, let's do another one. Here is CO with a 2+ charge. You're going to have to look up its name. Yeah, Cl with a minus charge. You'll have to look up its name too. What I want you to do is write the ionic compound in terms of its formula based on the ions that are there, and then give it a name. So first write the formula, and then write the name of it. So putting these together, you should have gotten this for its formula. It looks like people are, so that's good. Now give it a name. So this is cobalt off the periodic table, but because it is not in groups 1 or 2A, nor is it aluminum, we have to include its charge as Roman numerals. So this would be cobalt 2. And the Cl minus becomes chloride. And my text just appeared all over, but that's okay. Boop, there we go. All right, let's do one more. Do the same thing for this pair. What's the formula, and then what would you name it? All right, so we got MnO PQRSTUV WXYZ. No, just MnO. And then we gotta name this guy. Again, a transition metal, so we gotta include its charge in the name. This is manganese 2. And then this is oxide. There you go. So this is pretty straightforward. And in fact, this is about as difficult as it gets in terms of the complexity of naming stuff. So covalent compounds will have their own gimmick, and then acids will have their own gimmick. But the problem that people run into is that they all get mixed up. All the rules are very similar, and it becomes very difficult to differentiate them. Do the best that you can to make sure that you are using the right rules for the right compound. And again, the way to do that is to categorize your compound before you start. Which one of the rules should I use? Okay, here are the rules. How come I don't do the -2 and O2 minus? Because oxide is always -2, so it's implied. Because O2 minus will always form the 2 minus ion. Oxygen won't form any other ion because it follows the octet rule. Same thing for sodium. Sodium always becomes +1, so we don't worry about its charge in the name because it's always going to be sodium 1. All right, let's give you a bunch of examples here. I don't know why they're not in blue, but that's okay. So I want you to name these compounds. None of these have transition metals in them, so these are all the group 1, group 2, and aluminum ones. And then on the next page, I'll give you the ones that transition metals, and you can put it all together. Okay? So I'll give you probably like 2 or 3 minutes to type out your answers into the chat, or write them on your paper or whatever. And we'll go over the answers together when I get back. See you in a bit. Now, something to note, because you are going to have to type these into Canvas, and this is a common mistake that people make. Elements are not proper nouns, so you don't capitalize anything but the Roman numerals. In fact, Canvas will mark you wrong if you do that. So be careful that you don't capitalize the first letter of each element name, because, again, they're not proper nouns. But otherwise, your answers look pretty good. We'll go over the answers in just a second. All right, let's go over the answers. So I gotta clear this part. So let's start here. So for number 1, Li is lithium. And O is oxygen, which becomes oxide. Number 2, Be is beryllium. And Cl is chloride. More specifically, Cl is chlorine, which becomes chloride. Al is aluminum. If you're British, it's aluminium. That's fine. Either spelling is okay. O is oxide again. There you go. K is potassium. And I is iodide. Potassium iodide is an important nutrient for your thyroid. Make sure you get enough. Let me trim this down and we'll get this out of the way. All right, so now I want to give the formula of the following compounds. Now, the easiest way to do this is to take the name and then turn it into the ion that it represents. So for strontium, I would go, okay, this is it on the periodic table. What ion does it form? Well, it's in column 2, so it must be 2+. Bromide is bromine as an ion. It's in group 7. It needs 1 electron to get its octet, so it would be that. And then you can put them together to get the formula. So this step right here, this is Unit 9. So if you're looking at this and going, oh, I don't remember how to do that, it's time to review Unit 9. All right, rubidium nitride. I'm going to run out of space here, so I got to scroll this down. Rubidium is Rb. The ion that forms for rubidium is plus. Nitride is nitrogen. The ion that it forms is -3. And if we put those together, we get Rb3N. For the next one, sodium. Sodium is Na+. Sulfide is sulfur with a 2-. There's the formula, Na2S. And then magnesium is 2+. Iodide is iodine with a minus. MgI2. There you go. That's how we turn names into formulas and formulas into names. Is aluminum oxide the base unit for rubies and sapphires? It is, actually. However, aluminum oxide as a compound is colorless. You actually need like chromium impurities to make rubies and sapphires get their custom blue and red colors. So it's due to the impurities in a very regular fashion that gives those gemstones their color. Aluminum oxide is colorless on its own. That's just a fun geology fact because I find geology fascinating. I've studied it a bit. In fact, that's the cool thing about transition metals is that a lot of them are responsible for colors in compounds. For example, cobalt is oftentimes pink or green. Titanium is usually very, very bright white. And then chromium is typically either gray or orange. There are other colors in there too. Vanadium's a bunch of colors. Copper's blue or green, and so on and so forth. Anyway, here's a bunch more compounds. Do the same thing. So take those ions and put them together and make a formula and then a name. And then for the bottom set, turn the names into ions and then also write a formula. It doesn't say to do that, but I'm going to add that here. So then write the formula. All right. So I'll give you a few more minutes to do that, and then we'll probably be due for a break. So I'll see you in just a bit. All right, let's go over the answers. Oops, I gotta fix that again. So, whoop. All right, so give the formula and the name. So if I take CO with a positive 3 charge and bromide with a minus charge, I would get that as my formula. Since cobalt had a 3 plus charge, we'll call it cobalt 3. And this part would be just bromide. For titanium 4 and then oxide, I would get, I'm going to actually write this one out here. You'll notice that you only need 2 oxygen ions here, 2 oxides, to cancel out the titanium 4 plus. So here's its formula. But it's really important to note that, yeah, this is titanium 4. That's its charge. So that's going to be its name, titanium 4 oxide. So be very careful that you don't look at the formula and try and assume something about the ion. Break the formula into its ions, because the ions are what help you figure out the name. Finally, we got chromium 2 and then sulfide. So chromium 2 and sulfide would go together to make a curse. That's what that is, right? So there's chromium 2 and then sulfide. Sulfide, there we go. All right, that's the first 3. Let's do these last ones. Write these ions and then write the formula. So we'll just scroll this right down. So we got gold 1 chloride. So that means that for gold 1, I got to write down its symbol. If it's got a 1, that means it has a +1 charge. Here's chloride. So I can put those together, and then there's the formula. For sodium nitride, here's sodium. Here's nitride. There's the formula. Barium has a 2 plus charge. Oxide is 2 minus. There's the formula. Same thing for platinum 4. Platinum with a 4 charge. Fluoride. There you go. All right, looks like people in the chat are doing well on these. And that's all you do for ionic compounds. Now, one thing to comment about is when you are typing the name into an answer field in Canvas, spelling does count, obviously. If you misspell your compound, you get the wrong answer. What I try and do specifically for naming is I give it a prompt where I say, allow a certain number of keystroke mistakes. Usually that's on the order of like 2. So if you invert any 2 characters, I accept it as the correct answer. But if you omit a character, then it's wrong. Okay, so just be very careful that you are not making a spelling mistake or putting the wrong Roman numeral in or putting them in the wrong order or something like that, okay? Be really just sure of your answer. Double check it before you submit. Okay, so before we go on to polyatomic compounds, which is actually the same thing, we're going to take our break. So let me put the timer up. Boop, there it is. We'll move it up there. I'm going to start the timer and then find more Mega Man music. And I'll see you in about 10 minutes. Back in a bit. Oh, that wasn't even close at all. That's too bad. All right. Hi, everybody. Welcome back. Let's talk about polyatomic ionic compounds. Polyatomic ionic compounds are actually a lot easier to name because you already know their names. They're on that slide that I put in Unit 6. Should say Unit 6, not Chapter 6, but same thing. All you do is drop the name of the polyatomic ion into the box. You don't change it in any way. So even if the ions for many of the polyatomics, they don't end in "ide." In fact, almost all of them, none of them end in "ide." You're just going to drop its name right in there and not change it at all. Okay? So let's do some examples of this. Now, this is going to require you to go and get that slide and have it handy. So what I'm going to do is I'm going to open that slide. Which would be in this chapter. And let me see if I can capture that. Oops, that's not OBS. So window capture, I want to capture this. I'm going to show this really quickly, but then I'm going to... I actually don't know what the resolution on this is going to be when I blow it up, so... In fact, it may be unreadable. That's not great. Give me a second. Hold on. So... I can make this... Oops, why isn't it working? There we go. So if I do this... there we go. Now it should be readable. All right, so this is the slide from Unit 6. So I'm going to leave that on the screen for just a second so you can find the one you want. But you're going to want to refer to this slide on your own. And then now I'm going to go like this. Boop. And there's the problem that you want to look at. So there's I almost said the answer. There's having my little Arnold Schwarzenegger moment here. So what is the name of this molecule based on that chart? So now K is potassium, that's good. And then you found permanganate, which is right in the middle there. And yeah, it's difficult to spell it, which is why I allow you that flexibility. Like, oh, I typed one letter wrong, that's okay. So very good, it is potassium permanganate. Let's do another one. How about this? So now you got to find out what part of this is the polyatomic ion. And then you got to find it on the chart. So now that you've looked at that, yeah, be very careful you don't do Canvas quizzes on your phone, because your phone will autocorrect stuff. Also, capitalization matters, and trying to type capitalization on a phone keyboard is obnoxious. So now you got the name of this written down. I'm going to go bloop, put this back on the screen. I should notice that this one might not even be on there, but you can apply the same type of logic. I didn't actually put bisulfite on your list here. Oops, yeah, don't worry about this example. That one's not on the list, because you'll notice that right here. There's only a 3. So I could talk a little bit about the polyatomic ions really quickly. So whenever you have an H in front of a polyatomic ion, you append the prefix bi, or you could say hydrogen sulfite for this one. Sulfite being because it's got SO3 2- in it. So, not the best example. I gave you one that wasn't on the chart. But these ones are on the chart. They just might be on the next part of the chart. Let me put all of them up here. Now, obviously, I'm not going to put the chart on the screen because it would cover up the entire thing. And this isn't even the whole chart. Like, there is a second page. Remember that. So, refer to the slides in Unit 6 in Canvas. And what I want you to do is tell me what the names are of those first 4, and then write the formula of those bottom 3. Okay? So, do the best that you can typing that into the chat. And we'll go over the answers together in just a moment. How are we doing? There's a lot of answers in there, so let's go over them. I have plenty of space on this slide, so I'm just going to write directly on it. All right, so looking up this, NH4, you'll see that it has that as its ion. There's two of them, and that's good because SO4 has a 2- charge, so they go together. This is ammonium sulfate. And that should be a lowercase s. I'm bad at writing. Here we've got K, which is potassium. And then this thing, which when you look up what that ion is, it's on page... Is chloride on page 2? Let's see here. Boop. Oh, no, it is on page 1. Boop. So this is chlorate. It's the bromate and the iodate that are on the next page. This third one is bacon. No, not really. So it's got barium in it. And then the last thing is I couldn't save that one. I have to try that O again. Carbonate. There you go. That's not a very good E either. Why don't we capitalize it? It's because none of these are proper nouns. Like, they're not actually names. They're just terms that we ascribe to them. It's kind of like how we don't capitalize adjectives. You could think of these as adjectives. They're just regular old nouns. We got lithium for this next one. And we got this crazy-ass thing. Cr2O7. If you look that up, that is dichrome 8. Wow, I'm really doing a great job at the letter E today. Good job. All right. Turning names into formulas is a little more difficult because you got to start looking these things up and then pairing the ions together in the right way. So sodium's easy. That's just Na+. Hydrogen carbonate, though, we got to look that up. And importantly, we need to put the minus charge on it. When we put those together, you get NaHCO3. Do I need parentheses? Well, since I only had one hydrogen carbonate ion, I don't need parentheses around it. So this would be correct as written. But if you did this on Canvas, it would mark it wrong. So don't use parentheses unless you absolutely have to. All right, so now we'll do ammonium, which is NH4+. Nitrite is NO2-. Be careful, it's not NO3, it's NO2. And then I need one each. Since there's only one of each polyatomic ion, I do not need parentheses, so we're good there. And then down here for potassium phosphate, we got K+ and PO4 3-, so those become K3PO4. There you go. That's how you do polyatomic ions. And putting them in ionic... Oh, excuse me, ionic compound names. Can I show an example when you would use parentheses? Sure. So, let me go to this screen here. Let's get rid of these. So an example with parentheses would be something like, let's see here. So let's say iron 3 carbonate. Let me do this so that there's a little more space here. So we know what iron 3 is. That's that. Well, we know what carbonate is. That's that from the polyatomic ion list. Now, how many of each do I need? Well, I'm going to need more carbonates to balance out the charge here. Another iron here. So now I have this right here is 6 plus. This right here is 6 minus. So these will balance out. So I have Fe2. And I have 3 of these carbonates. So I'd go parentheses carbonate 3. Oops, there we go. So here I would use the parentheses because I need 3 of them. But if I did this one instead, where I have iron 2 carbonate, you'll notice that, oh, they're the same charge. They're just going to cancel each other out immediately. And you're right. You wouldn't actually need to put a parentheses around that either. Okay? So that's when you would use parentheses, is when you have multiple of an ion that is needed. All right, that's ionic compounds. That's everything there is to talk about for naming ionic compounds. I'm in the wrong window. There we go. So now that you've learned all about how to name ionic compounds properly, what I want you to do is do these, I guess. I forgot that I had extra ones in here. Where's my slides here? Oh, this is just more on parentheses. Well, I have a bunch more of these for you guys to do. So here you go. I'll give you more of them to do. I was expected for that to be the last slide of the section, but I guess we're not done yet. I'm going to give you 2 minutes to do these, and then I'll come back. I'm just going to go fill my water. So we'll go over the answers shortly. All right, there we go. I have water back. It looks like some people are posting their answers, so we're good. I'm going to just write directly on the slide. We got calcium sulfate, so here's calcium. Here's sulfate. Just put them together. 2 plus 2 minus, so let's cancel out. Just need 1 each. Here's rubidium, Rb plus. Hydroxide is OH minus. Nickel 2 is Ni2 plus. Cyanide is Cn minus. I'm going to need 2 of these. Whoops. We'll just fix that. Now that looks dumb. Boop, boop. There you go. Molybdenum 6 is Mo6 plus. Phosphate is PO4 3 minus. I'm going to need 2 of these to cancel out the 6 plus. And there you go. MoPO4 2. With parentheses in the appropriate spot. The last slide in this section just goes over when to use parentheses. So whenever you have more than one polyatomic ion, like we've been doing so far, make sure you're using parentheses. Make sure you're writing it correctly. I'm going to leave these problems on the screen here for you to do as practice on your own, because we're going to move on to covalent compounds, which doesn't take very long, and I can do that in 20 minutes. So, and we'll do acids on Thursday, and then we'll start Unit 12. All right, so let's talk about molecular compounds. Molecular compounds follow a different rule, and you can see that the rule looks the same, but I've snuck something in here. And you'll notice that something I've snuck in here is, where's my highlighter? It's this thing right here. Now, I know that you don't really use the hashtag symbol to represent numbers anymore. But back in my day, the hashtag symbol was known as the pound symbol, but it also meant number sign. We also walked uphill both ways to work or whatever. I don't know, whatever. Kids, get off my lawn, that sort of thing. I'm old tomorrow. I'm allowed to make these jokes, right? So in those boxes, we're going to actually apply something related to a number. And the number is going to be related to the number of atoms of that type that we have. Now remember that these are both going to be non-metals. So when I am naming molecular compounds, I'm not naming a metal and a non-metal. I'm naming a first and a second element. The first element that's listed is going to be the element that is more metal-like. In general, that means the element that's furthest to the left on the periodic table. What if you have two elements that are in the same row? Well, then it's going to be the one that's furthest down, generally speaking. But there are some weird exceptions. The correct way to deal with this is to use a property called electronegativity. We don't talk about electronegativity in 140. We use it in 161. Electronegativity is how positively charged an element is versus how negatively charged it would be. We always arrange the more positive element first, and if it's ambiguous, don't worry about it too much. I will give you some sort of information that tells you which element goes first and which element goes second. But in any case, the first element that you use is always going to be named as is on the periodic table. The second element gets I'd on it just like it was an anion. It's not actually an anion because there's no charge. We're going to go into polymolecular compound naming. No, we're only going to name binary molecular compounds because you can't have polyatomic ions in a covalent compound because that would make it ionic. The more left and down on the periodic table, the more metallic it is. That's correct. Now, what about this hashtag that's in blue here? In that box, we're going to apply a numeric prefix that indicates how many of the atom it is attached to is present. This is where you get the things like di and tri and tetra and mono. So when you say carbon dioxide, it's because there are two oxygens in CO2. Now, importantly, you only use numeric prefixes for covalent compounds. Covalent / molecular. Those two words are interchangeable here, so just be mindful of that. Never use numeric prefixes for ionic. This is where people get screwed up. Is they see this rule and then they get it in their head, oh, I throw numeric prefixes everywhere. And then you start throwing di and tri and tetra around with metals, and that's not correct. So be careful. Okay? Make sure you're applying the correct rules to the correct compound. In your text online that I have linked, here is the table of nomenclature prefixes. These are the numbers that go in front of something and the number that it refers to. Now, you'll notice right here for 1, it says sometimes omitted. We're going to talk about this in a second. But whenever you have 3 of something, you put tri in front of that element name. If you had 8 of something, you put octa in front of it. 6 would be hexa, and so on and so forth. There are some spelling exceptions that occur to make things sound better. There's no reason that this is done other than, oh, it sounds stupid that way. I'm going to change it so it sounds better this way. Okay? Here are the exceptions that come up. The first is, if the compound we're looking at has only one of the first element, you don't use mono. So I would call CO2 carbon dioxide and not monocarbon dioxide. Likewise, if I had this compound, if I can get my pen out here, CO, ironically enough, they installed a carbon monoxide detector in my apartment today, finally, after 10 years of wanting one. Notice that we don't say monocarbon monoxide. We just say carbon monoxide. Now, there's also an interesting thing here. If the prefix is mono, where'd the extra O go? Well, if you end up with double vowels, some combinations get shortened. So, for example, AO and OO, we get rid of the prefix first letter to make it sound better. So we don't ever say pentaoxide. We say pentoxide, just so that there's one fewer syllable. Same thing for carbon monoxide. We don't go monoxide, because that looks stupid, and I can't handwrite anyway. Let me try that again. So this would be monoxide. You could see that this here, you could see the frowny face in that, even though I underlined it. It looks dumb. So what do? We get rid of the prefix last letter, and then just contract everything together to get monoxide. The last thing to note is, again, no Roman numerals, because these compounds don't have charges. In the previous section, we said use the Roman numerals for transition metals to figure out what their charge is. But that only applies in ionic compounds. In covalent compounds, there are no charges, so you will never use Roman numerals here. All right, let's do some examples. So what would this be called, and what are the number prefixes for each element? So first of all, look at N, look at O, look at the numbers. Give me a name for it. So this would be nitrogen. I don't know what happened to my T here. It looks kind of funny. Boop. Ow. All those letters were in one stroke. Nitrogen. There we go. And then there are 5 oxygens. That's penta. But we get rid of the A and just write pentoxide because we don't want an AO combo. Boop. There's only one AO combo allowed, and she's running for House of Representatives in New York, and she's awesome. That's my political joke for the day. How about SO2? What would I call this? Remember about the first element, when there's only one, what do you do? There you go. Very good. So this is just sulfur. Because there are two oxygens, we do dioxide. Now you might look at that and go, well, that's another double vowel, IO. Yeah, apparently we're okay with IO. We're also okay with II, so if you do diiodide, you do include both I's. If you got rid of the I guess it would sound too French or something. It'd be like dioxide. Or something hoity-toity like that. What do I call this thing? It's not water. Yeah, don't capitalize. Don't do it. The thing that kills all sorts of people. I mean, water can be deadly if you drink too much of it. In fact, we're going to learn on the next page about all sorts of reasons why DHMO should be banned, which is kind of fun. But an important thing to note here is that you might have noticed, well, like, wait a second, water starts with an H. Isn't that an acid? And the answer is not really. So water is actually what we consider to be the definition of the weakest possible substance that can still be an acid. But it's also the weakest possible substance that can be a base. It sits right on the line of neutral. So if you are a weaker acid than water, you're defined as a base. And if you're a weaker acid than a weaker base than water, you're defined as an acid. So water's kind of strange in that it just falls right on that category, and we had to just do something. So H2O is specifically the one example where H in the front does not refer to acid. Okay, and that's the only one you'll see. In fact, I won't even test you on water because it's water. Like, we're not going to use that common name. But this does bring out a very important point about naming stuff using a systematic method, because this is a very chemically sounding name, and lots of people who are maybe not necessarily very science background intensive or have not had the opportunity to study science might look at that and go, oh, that sounds kind of scary. Well, and this is particularly relevant to the upcoming election today, about misinformation. What I'm going to do is I'm going to try and convince you to ban water. And these are the reasons that I'm going to supply for banning dihydrogen monoxide. So, two things. A common name for this is hydroxyl acid, like we just talked about. So that's already scary. And did you know that this substance, dihydrogen monoxide, is the major component of acid rain? Ooh, that sounds scary, right? Most of acid rain is this stuff. Did you know that dihydrogen monoxide causes the greenhouse effect? In fact, DHMO is more of a greenhouse gas contributor than CO2. It absorbs more heat and would raise global temperatures faster. That's true, by the way. If you come into contact with dihydrogen monoxide, you can get severe burns. That'd be really bad. It's also deadly if you breathe it. Don't inhale it. If you breathe dihydrogen monoxide, you will die. It causes erosion. That's not good. All of our national parks, Grand Canyon, things like that, All of its erosion is due to this, completely. And it corrodes metal and rusts it. So if your brakes are rusty, it's dihydrogen monoxide. It's because it's all out there in the environment. And it can cause electrical failures, and it can cause your brakes to skid. So these are all terrible things. I don't want any of these things to happen. And yet, despite... Oh, by the way, 100% of people who have cancer have DHMO in them. Every single person who has ever had cancer has had this in them. Now, despite the dangers listed above, dihydrogen monoxide is often used in the following applications. We use it in industry all the time. We use it as a solvent and coolant. We use it in nuclear power. That's terrifying. We use it to make styrofoam, and we're environmentalists, so anytime we mention the word styrofoam, that's just bad, right? We use it as a fire retardant. Oh, no. We use it in animal research. Note that I've put the word cruel here because all animal research is cruel. We use it in pesticides. Even if you wash it, it's still contaminated. And it's in junk food. It's everywhere. And do you know why it's everywhere? Pardon my French, but it's fucking water. That's why. That's why it's everywhere. So everything I've highlighted on the screen here is something that is spun in such a way that it sounds scary. Like, holy shit, major component of acid rain? That's really bad. Yeah, if 90% of acid rain is water, and the other 10% is the acid part, I mean, it's called rain for a freaking reason, right? Yeah, if you breathe it, you will die. It's called drowning. Don't breathe water. Don't do it. Not recommended. So, all of these things are true. Yes, every single person who's had cancer has water in them because you need water to survive. It's important. In fact, I'm taking a drink of it right now. Nuclear power plants. Delicious. But the point of all of this is a lot of names with chemistry have a tendency to be used in such a way that their lack of knowledge, the lack of knowledge by the person who is hearing them, tends to get scared of them. And you can spin all this information in a way that is frightening. Okay? But look for the complete picture. Look for the facts and see what's going on behind the scenes. And don't listen to somebody just spewing out all of these things that sound correct, because there's always a darker side to all of this. And people are going to manipulate information in such a way that they're going to try and get you to do what they want with it. Because, like, in our example, voting. If we were going to vote to ban dihydrogen monoxide, and I only presented you with these facts about, here is a substance that does these things, would you ban it? And I think that a lot of people go, yeah, a lot of these things are terrible. And then the other half would be like, no, it's fucking water. What is wrong with you? In fact, case in point, they sort of did this experiment in, I want to say it was Atlanta, Georgia, on a radio station. It was for April Fools. And the radio station talked about all of these problems that dihydrogen monoxide was causing. And they even went so far to say, it's in our drinking water. And within an hour, they had been taken off the air because a mass panic had ensued. Because Americans are dumb. I'm just going to put that out there. Americans are fucking stupid. But it's not entirely your fault if you are unaware of what's going on behind the scenes. So do your research is the moral of the story. And don't be fucking stupid. That's also the moral of the story. Alright. That was appropriate that on election day I had to talk about that sort of thing. So I'm going to put these on the screen. What I want you to do is I want you to give the proper name. By the way, the name system that we're using is called IUPAC, IUPAC. I'll write that on the slide here. So, and that is the International Union for Pure and Applied Chemistry. So if you ever hear me say IUPAC, that's just what that means. Use the correct nomenclature for naming these 4 compounds, and then down at the bottom, turn the names into formulas. Generally speaking, these formulas are much easier to do in general with names. But be careful when you get to the ionic and covalent and acid part where it's all mixed together. Okay? So, again, just keep the rules in mind. We'll go over the answers in a few minutes. I'm just going to repeat what's in the chat here. So one of these compounds here, sulfur hexafluoride right here. Woo. I'm doing that with the mouse. I should probably just write that on here. Is really cool. And normally I'd show a video on it, but we don't really have enough time today. So I'm just going to make a little note here. Oops. That if you're watching this on YouTube, type that into your YouTube bar and then just like look around at some of the videos on it, because people will breathe it in and then their voice will get all deep. Or you can put it in like a fish tank and you can float stuff on it because it's denser than air. It's really cool. There's a lot of crazy stuff that you can do with it. And it's totally inert and it's totally safe. It's like a noble gas. Now, why is it totally safe? We'll talk about that in 161, actually. Now, something interesting, you might be looking at SF6 and thinking, well, wait a second. How does that satisfy the octet rule? If I have 6 things bonded to sulfur, wouldn't that be too many? And the answer to that question is, yeah, it is. It doesn't follow the octet rule. So you'll notice that you haven't seen some of these compounds when we were drawing Lewis structures. And you won't, because we're not going to draw them in 140. We only do simple Lewis structures. But there are bigger things out there that exist. So just a heads up on that. I got to write the answers in here because we're going to run out of time if I don't. So this is dinitrogen monoxide This is dichlorine trioxide. Notice that oxygen makes up almost all of these compounds. Oxygen is so abundant. So there's a lot of compounds that have oxygen in it. For fluorine, I remember that if you do OU, that's flour. So the other way is fluorine. And this is fluoride, actually. So U first before O. Otherwise, you get flour, which is what you cook with. And then we got 4 phosphorus, so tetraphosphorus, deca, but AO again, so decoxide. There you go. Personally, I think turning the names into formulas is easy, because di just means 2, and then boron, there you go, you're all set. Tri means 3, and then O is oxide. So there's your formula. And you just do that for all of them. And you're all set. Was that the last slide? It was the last slide. So that's all we're going to do today. All right, so what's coming up for this week? Tomorrow is lab number 3. I'm going to assign it. There's really not much to talk about lab number 3 other than, hey, here's a video that Samita made and I edited. Watch the video and fill in the worksheet. It's kind of like lab number 1, but you're going to be doing something different. But we'll talk about it a little bit, and then we'll just have Q&A time. Feel free to come out if you need questions answered from the previous chapter. Remember, there is a quiz coming up that's due on Thursday. So asking me questions from like units 9 to 10, that'd be a good use at that time. You can ask me stuff about naming. That's good too. You can ask me about lab number 3. Yeah, it's flame test. So the syllabus originally said properties of ionic compounds, and I was going to have you just mix stuff. But then I realized, like, that's going to look a lot like lab number 1, and that's kind of boring. So I decided to use Samita's flame test video because, 1, it's a little shorter, so you're not watching a 30-minute video. I took her 2 30-minute videos and made it into one 15-minute video. And the flame test is really cool. And it's applicable to fireworks, which is something that we do from time to time. America loves to set things on fire, particularly in July. And I mean fireworks and not like actual arson, but I guess that might be true also. When will lab 3 be due? It'll be due next week, so week 8. And then I'll assign you a lab in week 9. That'll be due week... I think that one's due week 11. And then the last week of class, we'll assign another lab during week 11, and it'll be due after the final exam. Lab 2 is still being graded. I'm working on it. It takes me a long time to grade the density lab because there's so many entries. When is the last week of class? I don't know. It's in the syllabus. December something. We have 11 weeks of class, and then there is a finals week. So whenever that works out on the calendar. Week 10 is Thanksgiving. There will only be a Tuesday lecture. Wednesday and Thursday are no class. I don't assign things to be due during Thanksgiving, so it'll be due either before or after. And yeah, so we're getting sort of close to the end here. The last thing that I do want to mention is that on Thursday, after we finish naming, it's back to math for the rest of the quarter. So we're going to be using math and calculations and calculators like crazy. So just sort of mentally prepare for that. And yeah, so that's where we're at. And that's all I got. So I want to wish everybody a good rest of the evening. Again, make sure that you go and vote. Hang in there mentally. Hopefully most of this craziness will be over soon. And then we won't have to stress out about the election anymore. And yeah, don't drink water. Or don't breathe water. If you inhale it, you will die. That would be bad. I don't want anyone to die. See you later. Have a good one.